Okay, so for this video, it's about transforming data. Okay, so essentially that means what happens if I multiply all the values in a data set by a number, or if I add all the values in the data set, if I add a number to all the values in the data set. And that's called transforming a distribution or transforming a data set. And especially if you have really, really large data sets, you don't want to have to recalculate the mean, especially if you made a simple error. Something like you accidentally used you're 1 digit off on every single value, or all you want to do is convert from centimeters to meters. And you don't want to have to necessarily go through and transform all the data if all you're looking for is what the new mean would be in the new standard deviation. Okay, and so this can be a very useful tool, and it should be pretty straightforward. It's just some general ideas. Okay, and this is standard 18, so we'll have a quiz on this on Thursday. It should be super easy. Okay, so we'll start with this very simple example. Suppose we have a couple elementary school students, and they're measuring their pinky length, and they found that their mean length of all the pinky lengths in the data set is about 4 centimeters. And they have a standard deviation of 1 centimeter. Okay, they're probably not finding the standard deviation, but let's say we find that for them. And then they also find that the median and the IQR are 3.87 centimeters for the median and 1 centimeter for the IQR. Okay, that's wonderful. But suppose the rulers were faulty, or perhaps even that their data collection was faulty. This is actually really common for students to start on the number 1 when they're first learning to measure, than instead of starting on 0. It's extremely common. So instead of us going and recalculating or transforming all the data and then just finding the mean, the median, the standard deviation, the IQR again, couldn't we just logically think through this? What would the new mean be? And what would the actual standard deviation be? And what's the median? And what's the real IQR? Okay, so let's think about this. And I'm going to go through kind of a logical proof here. Okay, so let's focus on the mean first. So remember the definition for mean. We have x bar is the sum of all the x's divided by how many data points we have, which is essentially just x1 plus x2 plus x3 plus dot, 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 all the way out to xn, divided by how many data points we have. And we're saying that that number is 4. Okay, 4 centimeters. All right, so what would happen if we added 1 to every single point? So I'm going to use this to find my new mean. So I'd have x1 plus 1, x2 plus 1, x3 plus 1, all the way out, dot, dot, dot. Things being weird. Plus xn plus 1, all divided by n. Well, if we look and see, we are essentially adding 1 n times, right? So this is really x1 plus x2 plus dot, 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 plus xn plus n times 1, all divided by n. We've added this 1 n times, so. All right, and this, we'll go right here, is the same as just the mean. You're just adding up x n times. So it's the sum of x divided by n plus n times 1 over n, which is x bar plus n's cancel. You're just adding 1. So what would my new mean be? It would be the old mean plus 1. It would be 4 plus 1. The true mean of the pinky length is actually going to be 5 centimeters. Okay, awesome, great. That's what the mean is going to be. What about the standard deviation? Let's check that. Okay, so our old standard deviation, going by our same formula, is the sum of x minus x bar all squared. Remember, x means all of the data points individually, and you subtract the mean individually, then you square them, then you add them all up, then divide by n minus 1, and then square root everything to put it back into the same units, essentially. Okay, but what about our new standard deviation? Okay, so I'm going to not write them all out because it doesn't really work that well for standard deviation like I did with the last one, x1 plus x2, because in this case, it'd be all the deviations squared. All right, but what I am going to do instead is say, well, really all I'm doing is I'm adding 1 to each data point, right? So it would just be the sum of x plus 1 minus, and remember we're using our new mean here, all right, because if I change the mean, the standard deviation changes along with it. And our new mean was x bar plus 1, all squared divided by n minus 1. But these ones cancel. So essentially, I'm just going to have x minus x bar all squared divided by n minus 1. And that's the exact same as the original standard deviation. So here, our new standard deviation is the same as our old standard deviation. Standard deviation didn't change. It was still 1 centimeter. Okay. Now, probably a little bit more obvious will be the median and the IQR. So let's look at that real quick. All right. So we want to figure out what the new median is. Well, it was just like if I wrote them all out in order, x1, x2, x3, dot, dot, dot. I got the median somewhere in the middle, dot, dot, dot. And then in the middle. And then I've got xn at the end, right? If I just add 1 to everything, that's essentially not changing where the position of the median is. It's still going to be that centermost point. The data point still, we're 50% below it and the 50% above it. So the new median would be the old median plus 1. Okay. So what was the old median? 3.8. So the new median would be 4.8 centimeters. Okay, so that's the true median. And then using this same logic right here, let's check what the IQR would be. Remember, the IQR is Q3 minus Q1. And remember, all I've done is added 1 to every single data point. So this is really going to be Q3 plus 1 minus Q1 plus 1. And I hope you can obviously see the 1's cancel. And it's Q3 minus Q1, so nothing changed. The new IQR is the same as the old IQR. And so let's see what happens here, right? So for our measures of center, which were the mean and the median, both of these essentially added 1 to their values, okay? So by adding 1 to every single data point, we added 1 to both our measures of center. For our measure of spread, which was the standard deviation and the IQR, simply by adding 1 to both of these units, it didn't change anything, or to all of the units, excuse me. It did not change the measures of spread, okay? So it's kind of like thinking if I had, here, I'll show you guys an example. If I had a graph like this, right? This is a graph of students guessing some values, okay? And for whatever reason, we transformed it, and there was some error. Maybe it was a 13-second delay or something, whatever, okay? And all we had to do was subtract 13 from each value. That's not going to change the shape of the distribution, which in turn directly would affect the spread, okay? This shape is generally going to be exactly the same. So simply by adding and subtracting a number will not change the spread, but you can see the center moved from here to here. Whereas before the center, the mean would be at 16 and now it's at 3, okay? Same thing with all of your data points, anything relying directly on the data points. But since spread is really a difference between the two data points, if I add something, they're going to end up canceling each other out, okay? So in general, here's our first rule of transforming data. If you're simply going to add a value A to every single data point in the distribution or subtract a value A, it doesn't matter, then the measure of center do not change, okay? So the mean, or excuse me, they do change. I didn't mean to say that. Then they would add A to every single mean, the median, the quartiles, the percentiles, every single measure of center. Okay, and we're about to go over percentiles, so don't worry about that so much just yet. All right, but however, what doesn't change is the spread. All that's done is that you've just shifted the graph, the histogram, left or right, but the shape remains exactly the same, okay? And therefore, if all I'm doing is adding a number, the spread won't change. Now, what happens if we multiply by a number? And this is really, really common, probably more so than simply adding or subtracting a value to the data set. And that's called multiplying by a scalar. If you multiply by a non-zero value, so you multiply by 0, it ruins everything. But how would multiplying by a number change the center or spread? And a really good example would be if, for instance, I measured something in inches and I need to now convert it to centimeters. How does the spread and the center change as a result of that? Okay, so I'll go back to our example for the mean. So if I do have something in inches and I want to convert it to centimeters, I would multiply everything by 2.54. So every single data point would multiply by 2.54, right? Okay, and then it would be in centimeters. All right, so if my old mean is the sum of x's all divided by n, which is x1 plus x2 plus dot, 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 xn all divided by n. The new mean would be 2.54 times every single one of those numbers. x1 plus 2.54 x2 plus dot, 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 plus 2.54 x sub n all divided by n. Well, I could just factor out a 2.54. And I'd have x1 plus x2 plus dot, 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 xn all over n. Well, this sucker right here is the mean. So it's really just going to be 2.54 times x bar. So our new mean is just multiplying by whatever that scalar is. Okay. And I'm sure you have an idea right now of what you think this new standard deviation would be. So the standard deviation formula is, again, the sum of x minus x bar all squared divided by n minus 1. Okay, so, and then square rooted it. So our new standard deviation, remember, is dependent upon our new mean. And what we've done, same logic as before, I'm going to take every value of x and multiply it by 2.54. And that means that my new mean is also going to be 2.54 times x bar, all squared divided by n minus 1. Okay, so what's going to happen here is I can factor out this 2.54. So I have 2.54 times x minus x bar. Oops, I forgot to write my x there. And then all of that is squared. So this 2.54 must be squared as well. So I'm going to have the sum of 2.54 squared times x minus x bar all squared n minus 1. And whether you remember this from pre-cal or not, these are, this is a scalar. And so all it would do is multiply it by the overall sum. And so what we would have is 2.54 all squared times the sum of x minus x bar all squared divided by n minus 1. And the square of a square root would just be 2.54. And this is just the standard deviation part right here with the square root there. So the new standard deviation would be 2.54 times the old standard deviation. So unlike what happened before, if I was just adding a number, that did not change the spread. But if I multiply by a number, I want you to think what's going to happen here. It's going to cause everything to spread out, all right, even further. So if my distribution sort of looked something like this, if I multiply all those values by 2.54, my distribution spread is going to be much greater, okay, because this value multiplied by 2.54 is now down here. This value multiplied by 2.54 is now down here, okay? This would be like assuming it would be at 0 or something. All right, so in general, what the rules are, okay, and I'm not going to go through how to do that with the median and the IQR because it's pretty straightforward. But if you multiply by a scalar, in this case, we're going to call it B, it will multiply the mean, the median, the quartiles, all by value B. So all of these, the new values would all be B times those numbers, okay? The measures of spread now also all multiply by B. And the shape will be quite the same, but the spread will be super, super, super spread out now. Okay, so that's how they're going to affect the shape in that way in terms of spread. Like it's still going to be a bell shaped, it's still going to be right skewed, but it's going to appear much more exaggerated because you're on a much larger scale now. Okay, one thing to take note of is the standard deviation. Since the standard deviation multiplies by b, the variance would multiply by b squared, since the standard deviation is the square of the variance. Okay, so here's an example. And so it's kind of tricky to say that it doesn't really affect the shape. In terms of it affecting shape, we mean that it's going to still be right skewed. It's still going to be bell shaped, etc. But like I said, it's going to be exaggerated. All right. So if here is our original values, and we wanted to convert them, we wanted to convert them all, excuse me, here's our original values in this case. And in this case, we divided them all by 3.28 in order to convert to meters. You can still, that we see, have this kind of very rough bimodal bell shape over here, but it's extremely right skewed. It's still going to be that case in both situations, all right? But the spread has definitely decreased if I divided by 3.28. If I started here, if I multiplied by 3.28, the spread greatly increases as well. In fact, it multiplies by 3.28. Okay. And we can see that with our means, and we can see that with all of our values. Here's our median here. We can see that with our IQR and our standard deviation. Okay, but what if you have multiple things going on? This is our very last example. If the mean of a distribution, so we're just going to call the distribution variable x. When we start to have a lot of distributions and we're comparing things, sometimes you call one of them x, one of them y, etc. If the mean is 30 and the standard deviation is 12, let's find this mean, and let's go ahead and actually find the standard deviation of z as well. And we'll find standard deviation of z. And let's go ahead and find the variance just for funsies. Let's go ahead and find this variance of z. So we want to find the mean of z, the standard deviation of z, and the standard deviation squared. But z is defined as if I took variable x, multiplied it by 3, and I added -2. Okay, so let's start by finding the mean. And in this case, this is a good lesson in notation. You can, like your calculator, or a computer program will always refer to it as x bar, and you can subscript to z, or because now our new variable z, you can call it a z bar. It doesn't really matter what you're going to do. I'm going to call it a z bar just because I feel like it. All right, it's the average of all the z's. All right, so the mean is affected by both adding and multiplying. Just follow your order of operations. If my old mean was 30, I'm going to do 3 times 30. And then I'm going to subtract 2. So that's 90 minus 2. The mean of z is going to be 88. Okay, but what about standard deviation? Remember, the standard deviation is not affected by adding or subtracting a value. The only thing that's affected is by scalar multiples. So the standard deviation of z, remember, all I have to do is take the old standard deviation and now just multiply it by the scalar, so it'd be 36. And the variance in the same regard, using all sorts of colors. Okay, I take the old variance. So I'm going to take my old variance and then I'm going to multiply that by the square. So remember, the old variance here of x would have been 144. Okay, so this is a little bit different. So the new variance would be 9 times 144, because you have to square root. Like, this is just the plain old 3 here. I have to square that number in order to put it inside the variance. It didn't have the square roots there. And it would be the exact same as if I just squared the 36. It's going to be real obvious. You can do whatever you want to do with that. And whatever 9 times 144 is. I think it's, what, 1036, something like that. Sorry, 1296. And again, this is really just a mathematical practice for you. It really serves no purpose. But okay, so your homework tonight is to finish to do the worksheet. It should not take you too long. Okay, you're just going to find the means, standard deviation, sometimes the median, sometimes the interquartile range, whatever, when you're transforming data. And that's it.